Hello everyone. So, we will start with Newton's method in this fifth week. We have learnt the line search algorithms, exact and backtracking line search algorithms, and among the algorithms that choose the directions, the descent directions, we learnt gradient descent algorithm and a few different forms of conjugate gradient algorithms, right. So, one using eigenvectors and the other the Fletcher-Reeves algorithm. In Fletcher-Reeves we also learnt the algorithms for quadratic functions and for any other functions, right. So, this week we will get started with Newton's method. So, Newton's method is slightly different when you compare it with the gradient descent and the conjugate gradient algorithms. Okay. So, maybe before starting with Newton's method, I would like to go through the what we discussed at the end in the last class, the Fletcher-Reeves algorithm for general functions, right. So, one thing that I did not do at the end of the previous lecture was to give an example for Fletcher-Reeves algorithm for general functions. I mean, I did give you a code for this particular algorithm when f is a quadratic function with its Hessian being positive definite, right. So, but nevertheless I mean we can also give an example for Fletcher-Reeves algorithm for general functions as well. We will use the same example. We will consider f of x x1 x2 equals x1 squared e power x2 plus x2 squared e power x1. Okay. So, we will use this function and just implement this algorithm just to show you how it is implemented. Okay. So, one thing that I can do is, since I have the frameworks developed from the previous codes, I will use them straight away here. So, I am going to now use now illustrate Fletcher-Reeves for general functions. Okay. Okay, maybe I should, yeah. So, yeah, these headings help us to understand what the codes are for. I mean, since we have written quite a bit of codes before, right. So, we will go to the place where we worked with, yeah. So, for gradient descent with backtracking line search, we defined f of x and grad of x, if you could recall, right. So, we will use the same code. I am not going to plot it. So, I am leaving this part as such. Maybe I will, yeah, I will copy these down. Okay. And of course, I will explain I mean what each lines do anyway. So, yeah, this is not needed, and yeah, I am not going to plot these as well. So, we can leave them as well. We will leave these y1 y2. Yeah. So, yeah, there are a little bit of changes that will be needed. We will get them done. So, we first define f of x, which is x1 squared e power x2 plus x2 squared e power x1, and the gradient has two components, as I have written them down here. Okay. And yeah, I am just choosing 1 comma 1 as we did for the gradient descent algorithm as well, and the values of k, rho and C1 are exactly the same. And yeah, so yeah, the condition is the same. So, we are just implementing this. So, we have initialized x naught tolerance k, and so this we have not done. D naught has not been initialized to minus G naught, we will do that right away. So, D is minus grad of x, that is the first step, and so this is fine. Now the backtracking line search is the same, alpha equal to 1, and so here I have to, so instead of x minus alpha into G, I have to write x plus alpha into D, because that is going to change, and minus f of x. So, this will be C 1 into alpha into grad of x dot D. Okay. So, that needs to be changed, and this needs to be changed as well. And here is I will tell you what I have done. I have initiated the while command norm g k greater than tall. I have chosen alpha k by backtracking line search. I have updated x k plus 1 as x k plus alpha k d k, but then this step is missing, right, the update of the direction, right. So, this we will copy down from what we have here, but this needs to be changed as well, we will do that. So, so these are going to be grad of x minus grad of x plus grad of x dot grad of x, of course, that is g k transpose g k, sorry, g k plus 1 transpose g k plus 1, and here it will be okay. So, I have to do x old, which I forgot to do. So, here I can write grad of x old dot grad of x old into D. So, I have just written g k plus 1 transpose g k plus 1 by g k transpose g k, nothing great. Okay. So, the other one that I forgot to do is, so this has to be done when modulus of k comma n is not equal to 0. If modulus of k comma n equal to 0, this has to be just minus g k plus 1. So, this term should not be there in the first place, right. So, you can write it with an if command, right. So, if mod k n not equal to 0, then it has to be minus g k plus 1 plus g k plus 1 transpose g k plus 1 by g k transpose g k into d k, and if else it is just minus g k plus 1. That is certainly a method, but there is a shortcut which I am going to explain now. So, I am going to write it this way. If so, I am going to write this as k percentage 2. So, since n is 2 here, not equal to 0 into. So, what does this mean, just to just for illustration purpose. So, if k percentage 2 is not equal to 0, then this quantity will be 1, otherwise this quantity will be equal to 0. Okay. So, this quantity, right. So, the if part is implemented in this way. So, if k percentage 2 not equal to 0, then d will be the whole expression. If k percentage 2 is equal to 0, then this quantity is 0. So, all of this is going to be multiplied by 0. So, you will just get minus grad of x again. Okay. So, that is basically what is happening here. Okay. So, now we have the code, and let us compile it. Okay. So, in 30 steps we have got the answer 0 comma 0. Okay. So, you can use this code and just modify f of x grad of x and the initial point. Okay. So, that you can use this code for any other function that you want to find the minimum of. Okay. So, you can actually try a few other functions. So, you can recall the functions that I gave you in during the gradient descent lectures, right. So, yeah, as an exercise you can work out these functions, the Rosenbrock function with x naught equals 0 comma 0 and yeah. So, this you can work this out and yeah, you can again start this with 0 comma 0. Okay. So, yeah, I told you that you did not know the answer for when I gave this during the gradient descent lecture, but here yeah, I mean if you had worked that out you would know the answer. So, you can actually verify if you are getting the same answer or not. Okay. So, yeah, I wanted to do this before starting the Newton's method this week. Okay. Fine. So, with this we have I mean completed the discussion on conjugate gradient algorithms, Fletcher Reeves as well. Okay. Fine. So, and I actually started saying that while finding the descent directions you have a difference when you consider the gradient descent and the conjugate gradient algorithms when you compare it with Newton's method. What is that specific difference that I was talking about? Okay. So, you can recall that the I mean when we started with the optimization algorithms, right, we considered f of x as f of x k plus del f of x k transpose x minus x k, right. So, of course, this is not the Taylor series, the complete Taylor series, right. So, I mean this is the first order approximation of Taylor series, okay. And we used this expression to derive that del f x transpose d less than 0 is the condition for a condition that d should satisfy to be considered as a descent direction, right. So, the basis of all of the algorithms discussed until now, the gradient descent and the various forms of conjugate gradient, that is all based on the first order approximation. What happens if I construct an algorithm with the second order approximation? Okay. So, what is the second order approximation? So, yeah, this is the first order approximation of the Taylor series. Now, if you consider the second order approximation, it is okay. I will write it as del 2 f of x k right, or maybe a better way is to write plus half. Yeah. So, this is the second order approximation. So, Newton's method is actually going to be constructed using the second order approximation instead of the first order approximation. That is the very basic difference between the I mean earlier methods and the Newton's method that we are going to discuss today. Okay. So, fine. I mean how do we go about constructing Newton's method using second order approximation? So, let us consider I mean assume that f of x is equal to the second order approximation that I have written down here. Okay. Now, at the minimum, so let x star be the minimizer differentiating the above equation at x equal to x star, we have, so yeah, this will be del f of x star. So, f of x k does not depend on x, so the derivative is 0. So, here it depends on x only here. So, this will be del f of x k transpose, and the derivative of this is just del 2 f of x k into yeah, x star minus x k. Okay. But we know that since x star is the minimizer, del f of x star is actually equal to 0, right. So, this should be equal to 0, and therefore, x star minus x k is actually del 2 f of x k inverse, yeah, this is a minus, sorry, minus of del 2 f of x k inverse del f of x k. Okay, so, no transpose, sorry, yeah. So, we will in short write this as minus h k inverse g k. So, you know that del f of x k we usually write it as g k. So, from now on del 2 f of x k, that is the Hessian of f at x is equal to x k, we are going to mention it as h k. Okay. So, x star minus x k, which is, I mean the ideal direction that we want to travel from x k, right. So, that we are actually going to write it as h k inverse g k. Okay. This implies that we are going to choose the direction d k as minus of h k inverse g k. Okay. So, and from here the algorithm is very simple. Okay. So, because you now have got d k. So, if you recall, we were mulling over the choice of directions for a long time, right. So, if you recall our discussions on conjugate gradient algorithms, we were thinking a lot and working out a lot about how to find the set of descent directions in each step, right. So, here I have actually given an explicit formula which is minus of h k inverse g k, right, and alpha k will be 1. Okay. So, thus if you recall the algorithm that we had written very initially, I think here, yeah. So, this is the general algorithm that we wrote quite some time back, I think in the first lecture of 3rd week, right. So, initialize x 0 tol k equal to 0 while norm g k greater than the tolerance. So, you choose some descent direction, choose alpha k and so on, right. So, in every method we are only changing how we choose d k and how we choose alpha k, right. So, here I have actually given you the explicit formula, d k is minus h k inverse d k and alpha k is equal to 1, right. So, wonderful, then just let us just write down the algorithm. Okay. Newton's method algorithm. So, yeah, so we initialize x 0 tolerance and k equal to 0, and while norm g k greater than tolerance. So, yeah, so d k I have explicitly given the formula, alpha k also I have told as 1. So, x k plus 1 is just x k minus h k inverse g k, k equal to k plus 1, and you output x star equal to x k. Okay. So, at least looks very simple. Okay. So, We have quite a few questions regarding, so yeah, the algorithm is very clear, nothing more to state here. One question that we need to answer before moving to examples is whether this direction that we have chosen minus hk inverse gk, is it a descent direction or not, right. So, that is an important question, because if it is not a descent direction, then possibly we are not doing the right thing, is not it. So, our search is actually for descent directions. So, we have not shown that this if this is a descent direction or not, is not it. So, the proof is actually very simple. So, yeah, recall that a direction is a descent direction if del f of x transpose d is less than 0, right. So, this is the question that we are asking. If you are asking d is a descent direction or not, then we are basically asking is maybe I will write it with k. Okay. So, del f of x k transpose d k is less than 0, is that true or not, that is what we are asking. So, let us check. So, del f of x k is g k. So, g k transpose into minus h k inverse g k is, so you can see that this is less than 0 if h k is positive definite, right. So, what is the definition for a positive definite matrix? So, x transpose h k x should be greater than 0 for all x non-zero, right. So, here g k is non-zero, that is very clear, right. So, I mean if it is 0, then I mean we have actually attained the minimum and we can go home, right. So, g k is certainly non-zero, and yeah, so if h k is positive definite, then h k inverse is also positive definite, and minus of h k inverse is negative definite, right. So, when you have x transpose A x where A is a negative definite matrix, then x transpose A x is always less than 0, right. So, there is a, so this is a condition. So, it is please note that if h k is positive definite, then we are actually having a descent direction, that I mean the expression here d k equal to minus h k inverse g k is a descent direction, otherwise it need not be a descent direction, please keep this in mind. Okay. So, but nevertheless if h k is positive definite, for example if we have a convex function, right. So, the Hessian of a convex function is always positive definite, right. So, if we have that, then yes, I mean every step in Newton's method is a descent direction, but if h k were not positive definite, then we are actually having a problem. Okay. We will discuss that shortly, possibly in the next lecture, but before that we will actually look at some examples, okay, of how Newton's method actually provides the solution. Okay. So, we will always start with quadratic functions, right. So, let us actually start with quadratic function here as well. So, we consider half x transpose h x plus b transpose x plus c, where h is positive definite. Okay. So, you can see that for this example del f of x is h x plus b, and yeah, so so that implies that the solution is so h x plus b equal to 0, which is minus h inverse b, okay, and del 2 f of x is just h for all x, isn't it. So, fine, I mean what this means is that we do not have to struggle too much to find the Hessian at each x k, I mean it is just straight away there, it is just h. Okay. So, let us apply Newton's algorithm, I mean theoretically, and then I will work out the code. So, theoretically you can say, so yeah, assume any x 0, arbitrary x 0, right. So, x 1 is actually equal to x 0 minus h inverse, yeah, h k inverse is just h inverse, and g k is h x plus b. So, you h x 0 plus b, sorry. So, x 0 is x 0 minus x 0 minus h inverse b equal to minus h inverse b. Okay. So, what does this tell us? If you want to minimize a quadratic function with any arbitrary x naught, okay, any arbitrary initial point, use Newton's method, it gives you the answer in just one step. No issues regarding the number of dimensions, no issues regarding I mean the eigenvalues like what we had for gradient descent method, right. So, any quadratic function with any h, sorry, any positive definite h, right. So, you get the answer in exactly one step. So, that is how fast the Newton's algorithm is. Okay. So, I will just give an example, I mean do this quickly, I mean we have seen this theoretically itself, but let us also work it out practically, okay, I mean using Python. So, yeah, in this case you just need h, I mean you do not need to define f of x, grad of x and everything. Okay. So, I will just copy this code. Okay. Fletcher Reeves with exact line search, right. So, yeah, so I also want to write down what this means. So, this is Newton's method for quadratic functions. Okay. Yeah. So, again I am initializing A as some random 5 cross 5 matrix, H is A transpose plus I, this makes H a positive definite matrix, X also I am choosing randomly. Okay. You do not need D here, this is just print. Okay. And yeah, so the while command is the same. So, all of these are not needed. So, you just modify this as minus np dot linalg dot inv of h at okay, grad of x is actually h x. Okay. So, in fact, I could add b also. So, I will do that. So, b is just again np dot random of 5. Okay. So, okay, in that case I will have to modify this as h x plus b and this also as h x plus b, right. So, this is also not needed. Okay. So, let us check if it gives the answer in one step. Yes, that is it, right. So, I will also print okay, h inverse b just in order to prove that we have got the same answer. Okay. So, let us write something, let us say yeah, solution is okay. So, or maybe I will just write y, so that it is easy to replace here, otherwise I have to type SOL every time. This is not needed and k is also not needed. Yeah. Yeah. So, just to show you that the answers are oh okay, I think I should have written minus minus h inverse and now I am getting the negative, oh yeah, this is minus, yeah. Yes, so here you go. So the answers are minus 0.028, minus 0.0087 and so on. Similarly, here you have the answer. Okay. I mean this is just to show that yeah, the answer for the random h and b that I generated is y, which is below, and what I have got by the algorithm is exactly the same. Okay. All right. So, yeah, this is I mean appears like a very nice algorithm, because I mean, so you just had the answer in one step, what we were mulling over for quite long in the previous lectures, right. So, fine, we will discuss one more example and then move ahead with the issues with this particular method. Thank you.